different things, okay? The number of inhabitants in the city, the income measured in, I don't know, in thousands of dollars annually, in average of the inhabitants of the city, the rate of unemployment, and the number of murders per million, for instance. Yeah, we have all this information in our training data set. Yeah, the training data set contains several cities with this information, and the thing that we want to do in this case is supply regression. Okay, in this case, we will try to predict the number of murders with respect to other variables. Okay, in particular, we can use all the columns linearly in order to predict the number of murders, but we will start from simple and we will use only the income to predict the murders. Okay. Yeah, the models that we will use for this are linear functions. Okay, that means polynomials of degree 1 only. Okay, they are very, very simple. Okay, but let's just start with this and later we will complicate it. So, yeah, this is each point on this in this graph represents a city. Okay, this city has this income and this murder and so on. And in this case, the regression line that explains or predicts the murder with respect to the income is this one. Okay, you have the line here. But how can we obtain this? This line is the best line that describes our line. Okay, but let's see how can we obtain this kind of lines. There are two ways to find the solution, this kind of line. One that is the optimization way. That means we will have a loss function that we want to optimize. And later we will see another way to do this, that is the probabilistic way. In the probabilistic way, we will see how we can represent with a probabilistic model or data, and we will try to find the best parameter that maximizes the likelihood of the model. We will see that later. Okay, but let's just start with the optimization. Okay? So, first of all, we have to consider the kind of solutions. Okay, the kind of solutions that we will use in this case are of this kind, linear equations. Okay? In this case, this linear equation, when we only want to predict one value in terms depending on another one, then we have this linear solution that is basically a line, and this is the slope of the line, and this is the offset of this. This line is up or down. Okay? So this equation here, in fact, is represented in this way. Okay, this is a line. Okay? This is the slope, depending on the value of the slope, then you have one line or another one, and depending on the offset, you have one line or another. Okay, that's it. So this is the model that we would use to predict the data. Okay, and this model has these two theta parameters that values that are the parameters of the model. What we call it or name it before the coefficient, the polynomial. Okay, in this case is what we call the parameters. And in general, we will talk about the parameters of a model as the model is a line, and the parameters are the actual values of the line that defines the model. Okay? So if you have two values, theta 0 and theta 1, then you have one model. If you have different values of theta 0 and theta 1, you have a different model. Okay? Linear models, but different. Okay? Because the parameters are different. In particular, this line is defined only by these two parameters. Okay? Theta 1, that is the slope, and theta 0, that is the offset. Okay. So that's important. These are the parameters of the model. So in fact, if we want to obtain a regression line, yes, we know that the line has this form. The thing that we have to do is to find the best parameters for the linear, this line. Okay, the best parameters. So the best parameters are the ones that define this line here, and that corresponds to the slope of this line, and so this line is the offset of the line. Okay. So yeah, we know that this is the solution. We have to find the parameters, but how to find the parameters? How can we find the parameters? Well, from the machine learning point of view, the thing that we will do is first define a loss function. Okay? In this case, the loss function, the thing that we want to minimize, is the squared error. Okay? And the squared error means the difference between the predicted error, the predicted value, and the true value for each of the 20 cities, okay, that we have in the training data set. Okay, so I have a training data set. In this data set, I have 20 cities, and for each city, okay, I have one predicted value and one true value. I will compute the difference and square it. And I will sum these errors, these differences, for each of the 20 cities. Okay, so this will be my loss function. Notice that this loss function depends on the parameter. Okay, why? Because this prediction, in fact, is this linear equation. Okay, so in fact, if we replace this white hat with the definition of this linear equation, then we have that we want to minimize, well, this is the error that we have associated with these parameters. And the thing that we want to do is, of course, if this is my loss function, the error, how I measure the error, the thing that I want to do is to minimize this error. Okay? So the thing that I have to do is very simple. The thing that I have to do is to find parameters zeta 0, zeta 1 that minimizes this function. Okay, this error. Okay, this is what I have to do. Okay. Okay. So yeah. So how can we do this? Well, this is the picture of what is happening now. Okay, so I'm finding the best parameters, the parameters that have the pair of parameters slope and offset that minimizes this error, and this is the line that corresponds to this. Okay. So how to find these parameters? One thing that we can do is, okay, I have an error function, I want to minimize this function, so something that I can do is to derivate the error function with respect to the parameters and equate this to 0. Okay? So this is something common in optimization. Okay? When you want to find the minimum of a function, in this case this function is convex, so we only have one minimum. The thing that you have to do is to derivate, okay, with respect to the parameters and equate this to 0, and then define the parameters that satisfy that this derivative with respect to the parameters is 0. And that's it. Okay, and this is what we will do. But, first of all, we will move to the more complex way, the more complex problem, where instead we will try to generalize. Instead of using linear models that only depends on one variable to predict the other one, okay, instead of using only the income to predict the models, the thing that I will do is to build a linear model that uses inhabitants, income, employed, and so on to predict the model. Okay? In this case, the linear equation is not this one, it's this other one. Okay? So this is column 1 that I think that income, the second one is the inhabitants, and the third one is the unemployment rate. And with this information, I want to predict the models. Okay? This is again a linear equation. Okay, we don't have monomials here of degree 2 or 3 or whatever. We only have the degrees, the maximum degree is 1. Okay. And now we will use all the information that we have in the table to predict the models. Okay? So this is my linear model, but let's try to generalize a little the things. So the thing that I will do is, okay, we separate the first part with the rest. So here we have zeta 0 that is added to the sum of these three terms that can be represented in this way. This is parameter g, okay, this is parameter 1, 2, 3, so g goes from 1 to 3, and I'm multiplying, if I want to predict row number I, then this is xi, multiply it by zeta, where zeta is the parameter that goes 1 to 3, okay, 1 with 1, okay, 2 with 2, and 3 with 3. Okay, this is exactly the way to represent this. Okay. Okay, so yeah, that's easy. So, however, this is not perfectly nice. So, why? Because we have two different terms. So the thing that we will do is to add this theta 0 into the sum. And then we will expand. Instead of starting in g equal to 1, we will start in g equal to 0. But if we start in g equal to 0, then what's x, y, g? Okay, x, y, g will be the constant value 1. Okay, so this is for g0, 1 multiplied by zeta 0, that will be this term, and the other ones will be exactly. So we will add a special column that is this 1, this column here, that is column 1, that represents, that is the one that I need to compute in the same way than the other one. Okay? So if this is my table, this will be my x data. Okay? That is exactly my information without the thing that I want to predict. This is the column that I want to predict, and this is my data. This is my data with this extra column 1. Okay? And just to do things more compact and easier to compute. Okay. So, yeah. Then this is what I want to predict. This is what usually is named the label, and this is my data. And then the thing is that my linear model in this way can be represented as the product of matrices. Okay? This is the prediction is the matrix of my data with this one column multiplied by the vector of parameters. Okay? The vector of parameters is this one. You have all the parameters here. Okay? And notice that that's easy with this product, because this product is this number by this one by this one, and so on, and this gives me the prediction for the first value. Then the product of the second row with the parameters gives me the second prediction, and so on. So we are writing exactly what we had in here, but in matricial form. Okay? So that's my notice that here we don't have the zeta 0 because we have this one parameter. Yeah.
And your coefficient theta 0 is the actual value, correct?
Exactly. This is the zeta parameter is the offset, how you move up or down your line. Okay, and this can be seen as zeta 0 multiplied always by 1. Okay? And that's why we are representing this 1 that is always multiplied by zeta 0, which is what is represented here. Okay? Okay, so yeah, so let's do some maths about this. So yeah, we have the thing that I want to minimize. Now this is my loss function, the thing that I want to minimize. These errors that is computed as the difference for all the 20 points that I have in my training data set. In general, if n is the number of rows that I have in my data set, is the sum from 1 to n of the differences between the prediction and the true value squared. Okay? So, yeah. So, this number can be represented in this way. This squared can be represented as the differences between the labels and the predicted values transposed multiplied by the values, the true values minus the predicted values. Okay? Yeah, because this is if you do this problem, you will see that this is a scalar number, this positive number, and that is the sum of all the atoms. Okay? Yeah, replacing the predicted label with the actual equation that we derived here, okay, the data multiplied by the parameters, then we have this equation. Okay. So we said we want to minimize the error. So the thing that we will do is to compute the derivative of the error function with respect to the parameters and equate this to 0. And the parameters that fulfill this equation will be the ones that minimize the function. Okay, this is done usually in optimization. Okay, in order to do that, we have to remember that the derivative of a multiplied by something, in this case, this is the parameter of the x, okay, with derivative with respect to x, in this case of theta, is divided or with respect to the derivative of the parameters, is the transposed of the matrix, okay? And in this case, that is this quadratic term, where we have the parameters multiplied by a matrix and the parameters, it's like we're having a quadratic term, then is 2 multiplied by the b, that is the matrix, multiplied by this is the parameters. You can go back to or you can go to books about derivation with matrices and so on, but this is where we have, okay? So this is the derivative of the error function with respect to the parameters. This is the function is this one, so this is what we want to derivate with respect to the parameters. And if you do this, well, you do the products before the derivation. So this by x is it multiplied by e, because this I is transposed. Then we have minus this term multiplied by this term, minus this term multiplied by this term, that is these things up here, and then this term multiplied by this term, that is the theta transposed multiplied by x transposed multiplied by x, and theta. Okay? So now this is only doing the products, okay? This is the expansion of these products, and now we can derivate with respect to the parameters. The thing that I'm doing first is adding these two terms, okay? So this plus this is 2 times 1 of them. And the thing that I do now is to derivate with respect to the parameters. Here we don't have the parameters, so this is a constant term with respect to the parameters, so it disappears. It's a 0. And then you have this term. So yeah, here we have this something multiplied by the parameters, derivated with respect to the parameters is this thing, so it's this transposed, okay, that is this thing of here, and plus the derivative of this, remembering this derivation rule with matrices, and then the thing that we have is 2 times, this is the 2, b, where b is the thing that is in the middle of the product of the parameters, okay, this is b, and this is the second parameter. So, yeah, this is the derivative of the equation with respect to the parameters. And then the thing that you have to do is to equate this to 0. Okay? So if 0 is equal to this thing, you can move this part to the other side, and then you have this term. Okay? And then you can remove the 2 and the 2 of both sides, and then you can multiply also in both sides by x transpose and multiply it by x, the inverse of this, multiply this from the right. Okay? So if you multiply here by this term, okay, this will be the identity, so you will have only the parameters. And then this other part also has been to be multiplied, from this part. Okay, so this term appears here. The 2 has disappeared before, so this is the solution to my problem. Okay, so yeah, we did a lot of matricial derivations and so on, but the idea is that yeah, we can compute analytically the solution of the best parameters for the linear regression. That is simple. The only thing that you need is to get the matrix data, transpose and multiply it by x, obtain the inverse of this matrix and multiply this by the transpose of the data and by the predicted labels. And this is the parameters that minimize the error function. Okay? So that's the solution. Okay? This is how we can do things. This is the optimization way. What I mean with optimization way means that we are using techniques of optimization, like saying I have a function that I want to minimize, so the thing that I will do is to derivate this with respect to the parameters and to find and to equate this to 0. Yeah?
And here your theta least squared error is still a matrix, right?
Sorry?
Is your theta least squared error still a matrix? So you
Yeah, this is a vector.
Yeah, or a vector, yeah.
It's a vector. Yeah, this is again in matricial form. So this is a vector, this is a matrix, this product of here is a matrix, and y is a vector. Okay. Okay. So yeah, once you have computed the best parameters, okay, then least squares error, this is the term that I give to the optimal parameters applying this method, okay? Then if you find the solution and you want to apply the solution to a new point, an unseen data, then the only thing that you have to do is to, this is my unseen data, a new city, okay, that has an income, number of inhabitants and so on. That you want to predict the number of marbles, so this is my data. That the thing that I have to do is to add a 1 because it will be multiplied by theta 0. These are the parameters that you have found, and if you do the product, you will see that you obtain the linear prediction with the parameters that you have found. Okay? So steps. First, define the error function. In this case, we have defined the difference, the squared errors, okay? And then the thing that we have to do is to optimize this error function because we want to minimize the squared errors. And then we did this using optimization techniques, and then we have the parameters. We have found the parameters to do predictions for new data. Okay. However, we have several problems here. The first problem is that we have to invert this matrix, and the inversion of this matrix in some cases can be hard to do because if in this data you have columns that are not independent, repeated data or something like this matrix is not invertible. You cannot invert this matrix directly. Okay? So, even when they are independent but are very close, then you have numerical instabilities that makes it hard to compute meaningful values for the parameter. So, in practice, when we do this, instead of using this inversion of here, we do the singular value decomposition of the matrix. Okay? So the singular value decomposition of one matrix is simple. This is something that can be done on any matrix. The number of columns and rows that you have is not necessarily the same. Okay, so this does not need to be any square matrix. And then this is the decomposition. Any matrix can be decomposed in this way. Okay, to one matrix U that is where a matrix that has columns that are orthonormal. Okay, so the product of UT multiplied by U transpose multiplied by U is the identity. Then we have the sigma matrix that is a diagonal matrix of this kind. Okay, all zeros except on the diagonal where we have this sigma value. And then multiply it by this B transpose matrix that is something like this. And the idea is that this matrix, okay, can be decomposed on the product of these three matrices. When you see U here, this is a vector. Sorry, a column. Okay, so these are columns and these are rows. Okay, so in fact, this is not a vector. This is a matrix. Okay, and this is also a matrix. Okay. So this is something known in mathematics. You can always obtain a decomposition in this way of the matrix, and the idea is that we will apply this to solve the problems of the inverse of the matrix, of the original matrix. Okay. What we do is simple. The only thing that we do is replace this. This is the SDD singular value decomposition of this matrix xt divided by x. So the thing that you do is this is the decomposition of x, that the matrix x. Okay. So this we know. If x can be decomposed in this way, so the thing that we will do, this is this matrix transposed multiplied by x, that is this matrix, the inverse of this, and here we have this matrix transposed multiplied by x. The only thing that I have done is replacing every instance of x by his singular value decomposition. Okay, and then the only thing that I do is to operate here, and we end with something like this that is a lot simpler than the original equation. Okay, so you have B, that is the value decomposition. This is the inverse of the matrix, but this matrix is very easy to invert because this is sigma. Sigma, remember that is this diagonal matrix, and the inverse of the diagonal matrix is 1 divided by sigma 1, every other term is 0, 1 divided by sigma 2, and so on. So this matrix is very easy to invert. So yeah, here this inversion of the matrix is very, very simple, and then multiplied by UT and that's all. Okay, so instead of solving this problem, we solve this other one. Okay, and they are equivalent. Yeah.
If we're looking to minimize our error, would we not at some point need to take the second derivative to see if we're looking at a minimum or a maximum?
Yeah. That's true. I've done here an assumption, and the idea is that the thing that I assume it here, and that's true, is that this linear function is convex. Okay, by definition, it only has a solution, and this solution is a minimum.
Okay, so for this particular function that you're using, you can
Yes.
take this.
In other cases, you have to be sure.
Okay.
Okay, that's a good question. Yeah. Okay, so in Python, suppose this is done. Very simple. In NumPy, that is a package in Python, you have implemented this in the linear algebra package the singular value decomposition that returns you this U matrix, the diagonal, not the full matrix, not this, all the matrix, only the diagonal, and returns you also the dt, that means this vector transposed, okay? So, yeah, once you have found this, you have to create this matrix, the inverse of the matrix, that is, create a matrix with diagonal with vector g, and instead of creating the values with d, is 1 divided by d, because it's the inverse of the diagonal of this matrix. And then, when you have b, bg, then you have to transpose it again to obtain b, multiply it by b, that is the diagonal matrix, multiply it by u, that is returned by the SPD decomposition in NumPy transpose it, okay, and multiply it by and that's all. These are the parameters. So this is how to compute the parameters in NumPy for the linear regression, and this way to do the things, in this way we have more numerical stability than in the other case, because in the other case we had to inverse a matrix where we can have some collinearities there, and in this other case we only have to invert this other matrix, and in order to invert this matrix it's very simple because it's a diagonal. Okay. Perfect. So, yeah.
Just generally, is it important for us to be able to do this math by hand, or can I get by understanding what we're doing, and generally we're using Python to actually execute?
Yeah. Yeah. Of course, you don't need to do this, all this math, all these derivations that I have done, if you know the solution of it. Maybe somebody says to you, yeah, if you want to do linear regression, apply this formula and that's all. Okay, that's okay. From a practitioner, okay, from the point of view of somebody that wants to solve the data mining problem, this is okay. You don't need to do anything because you know the formula. Okay, that's okay. However, what we are doing here is explaining you how to do the right thing, how things are the right. Okay, so I'm giving you not this, not for this case that is well known, but also what we should do in other cases. This is an illustration of how to proceed in general. Okay, and the idea is define a loss function, try to minimize it using optimization, and then apply the function. Okay, so in this is well known, but in other cases when you have another loss function and maybe you have another model, then and you want to do that, and this is something that Ella has done before by anybody, or maybe you are not able to find the references, that you have to follow this. Okay, so yeah, from if you only want to apply a method that is well known, then you don't need to do all these steps, of course. Okay, but if you try to apply something new, this is how you have to proceed.
Why were we able to take the assumption that the search space of the optimization function is convex? Is it because it was a 1-degree function? Like 1 degree function?
Exactly, because this is a linear function and it's convex by definition. Okay?
But if it's a higher degree, then making that...
A quadratic formula is also convex, but a cubic formula is not convex. Okay? Yeah, more questions?
And sorry, I'll have to go back. I'll admit the math is way over my head today. And I'm guessing, I hope to God I'm not the only person in the room. But this function, am I defining anywhere within the NumPy side of things, like what order it's in? Or is that a parameter that I'm putting into this NumPy?
When you're using this, when you're using this, you're assuming that you're solving a linear equation. Okay? And this is the solution in NumPy for the linear equation. Okay? It only works for linear equations. If you want to find a quadratic model, then this does not work. But this is a good question, because what can happen when you draw this line? That, yeah, it can happen several things. One of them is that, yeah, you paint a line here that you can see that the errors are not equally distributed, okay, among these values. Okay, so for low values of x, you have low errors. For large values of x, you have larger errors. Or here, where we can see that maybe this point can be considered an outlier. Here we have a lot of points. If you look at the majority of points, then maybe you have a very different line. Okay? But you have a point that is very far from the other one, so the quadratic error of this point makes this line in this way. Okay, so this is not nice, and we will see later ways to solve this problem. And another problem is when you try to fit your data using a linear equation, you observe that in fact your model should not be linear. Okay, in this case, maybe a parabola would fit better your data. Okay, so yeah, we are using a linear function for fitting your data, but maybe your data cannot be fitted using a linear function, okay, or well fitted using a linear function because your data doesn't follow this linear distribution. So what can we do in this case? Well, we can do something that is a trick. The trick is not only working with the original data set, but also with an expanded data set where we also consider the quadratic terms. That means this is my original data set, 1 that is the column with 1, this x here, and then I will have more columns here. This is x power into 2, x power into 3, x power into 2. So you are adding more terms, more columns to your data set. And each of these columns are quadratic cubic terms of your data. And that's why this is interesting. This is interesting because this is the extension of my data set. And then the thing that I can do is, instead of doing linear regression on my original data set, I do linear regression on this expected data, this expanded data set. And then the interesting thing is that you can do this exactly the same way, using a linear equation. But notice that in this linear equation, you have parameters that are power to 2, to 3, and so on, because they are the new columns that you have added to your data. So you are doing linear regression. You can apply the same techniques that you have seen in linear regression, but in fact you are doing quadratic, cubic, and so on regression because you are considering these other terms that you have added, okay, explicitly in your data. Yeah.
So I see here that you were using linear for theta 1 and then quadratic for theta 2.
Yeah.
Does this mean that depending on which column we're looking at, we can choose which order we're going to use?
Yeah. Okay. The point is that your model does not know that this is quadratic term. This is something that a column that you have added that is a quadratic with respect to the original data. Okay. So the algorithm does not know it. Okay. So you are doing linear regression, and the fact is that if you do linear regression on this data set, in fact you are doing polynomial regression with degrees outside of it. Okay? Do you get that? Yeah?
Quick question, does this generalize to things other than polynomials, for example, with sines and exponentials and...
Yeah, you can do this, you can apply this trick to anything that you want, okay? So the idea is, okay, linear equations are limited, okay? But that you can apply these techniques that are very simple two other representations or data that also contains the symbols or whatever that our colleague is saying, or quadratic terms or cubic and so on. Okay? But the idea is that all these parameters are obtained in the same way. You only have to apply this. But now the X data set is expanded with these extra columns that contain the quadratic, the squared, cubic, and so on values of the data. That's nice. It's a trick that works very well. However, yeah, you have to compute these terms and these take times. It takes some time to do this. And we will see later in the final lectures a model that is called super vector machines that also applies this trick without having to explicitly define these columns. Okay, but it's okay. It's a nice thing. Okay, so the idea is that now this is my data, the prediction of my data, and then the solution is this one, applying linear a singular value of the composition as okay. So yeah, this is one way to solve the problem of linear regression. Okay, this is one way to do this. There is another one that can also be extended to other models. Okay, that is the probabilistic way. Okay, and that I will not have enough time to explain it today, so we will stop here. Okay, but there exists another methods to derive the solution, the right parameters for a model. Okay, and next day we will. Okay, thank you.